All right, I'd like to introduce our next presenters. Andrew and Yolnan are going to be presenting on the acoustic properties of the didgeridoo. So a warm welcome to Yolnan and Andrew.
So, hi, I'm Yolnan.
I'm Andrew.
And our project is examining the acoustic properties of the didgeridoo. So, first, our hypothesis is that if we change the physical properties of the didgeridoo, it would affect the frequency and amplitude of the sound wave produced. And our hypothesis is if we increase the length of the didgeridoo, that would decrease the frequency of the sound wave. And if we increase the diameter of the didgeridoo, that would increase the amplitude.
First off, the didgeridoo, it originates in Australia. It is formed when termites infest a tree and hollow out the branches. It is then cut off and then painted or decorated, made to look nice. It is a good example to study the longitudinal waves, which we'll explain in a minute. This is background information. Amplitude is the loudness or the intensity. Frequency is the speed of the vibration. It's measured in hertz. Frequency is basically how many times a wave of energy is produced. And here is the equation for it. At this frequency, lambda is equal to the wavelength here. The resonant number, we'll explain that later. And velocity is the velocity of the particles hitting each other to excite and pass the energy down the didgeridoo. So these are some examples. So higher frequency, the waves are closer together. Wow, I'm shaky. This is an oscilloscope graph. The y-axis represents pressure. So it's basically how dense the particles are in one specific place. And then obviously the x-axis is time. So that's how we find frequency sometimes. Pressure is measured in pascals. And it's directly related to amplitude. So as pressure goes up, as does amplitude. This is a little diagram of how the sine wave represents pressure. So when the level is down here, the particles are less dense in that area, and more dense and less dense, and it goes on. These red particles here with the traces are to show where the particle has been. So longitudinal waves, I mentioned them earlier. So basically why we chose the didgeridoo is because it is just basically one large air cylinder closed at one end, sealed by your mouth. So what happens when you play the didgeridoo is you put your mouth on one end and you basically just, and that's what we call oscillating. And that's how you play a trumpet or a tuba, and also how you play the didgeridoo. So with each time your lips hit each other, they produce energy, and those excite the particles in the didgeridoo. And how it works is they basically, one particle will be excited and will pass the energy on to the next one, and it will pass the energy on all the way down. So reflection, real quick. So when you play the didgeridoo, some of the energy, here, I'm actually going to draw a diagram here. Some of the energy comes down, so we have like nice waves here. Some of the energy comes down, and then when you reach the end, the pressure on the outside is different than the pressure on the inside. So some of the waves are reflected back. Some of them still come out, and that's how you hear things. So some of them come back, and then they reflect back, and then some of them come back again, and that's what we call standing waves. Reflection obviously is also caused when it hits a medium. Hard mediums reflect sound more effectively, and soft mediums absorb them. So impedance. This is the resistance of the energy to the airflow. Like I said here, some of the energy is transmitted and some is reflected. So it's impedance that causes standing waves to happen. So when it hits the end of the air cylinder or the didgeridoo, impedance causes it to reflect back because the pressure is different on the outside than it is on the inside. So this here is, we're going to show you a couple of these. This is how we got our results. This is a spectrogram. And basically what it does is it measures the frequency and the amplitude of a sound. So this here is what we call the fundamental frequency. This is the frequency that you hear the most of. So, if you are familiar in musical terms, that's the pitch. That's the main pitch here. These little spikes here are called the harmonics. They follow the frequencies at intervals of 4. So also, if you're familiar in musical terms, this is what you would call a sort of chord. So pitches, octaves, that sort of thing.
And to perform an experiment, we decided to make a soundproof box filled with insulation foam inside. That would reduce the background noise picked up by the microphone, which we have cut into, cut a hole into the microphone. And the microphone we connect to a laptop, which we have an application called OmniMic. And from there, we can monitor our spectrograms and oscilloscopes. And the graphs you've seen before, and you'll see later, are snapshots of one instance of the sound wave. And here are materials. We use PVC pipes of various lengths. One of them are 39.1 inches, and some are 48.9 inches. We also are box made out of particle board, and we also use our own didgeridoo, fiberbar mentor. And in this case, we are changing the length only to test how it affects frequency. All the other characteristics of the two PVC pipes are the same in thickness and diameter. So here is Didjeridoo 1, and Didjeridoo 1 is 39.1 inches long, while Didjeridoo 2 is 48.9 inches long. And you can see frequency is plotted on the x-axis, and Didjeridoo 1 has a higher frequency than Didjeridoo 2. And our next experiment, we compared how diameter affects amplitude, or how loud the sound is of the wave. And same thing as before, only thing that changed was diameter, and length and thickness were the same. So Didjeridoo 6 has a significantly larger diameter than Didjeridoo 7. And you can see here the amplitude plotted by the y-axis is much higher than Didgeridoo 7. I believe Didgeridoo 6 is around 130 decibels, while Didgeridoo 7 falls in 115 range. Next, we decided to test the effect of a bell end at the end of one of the PVC pipes. So initially, we had two Didgeridoos, 3 and 8. Didgeridoo 3 and 8 both initially had a 1-inch diameter, and we decided to add a bell end to Didgeridoo 8, which basically is like a cone in a sense, and the diameter increases near the end. And we want to see how that affected amplitude. So here, this is Didgeridoo 8, and you can see the amplitude is much higher than Didgeridoo 3.
Before we move on, we might want to explain how we know this. So the bell effect that we were monitoring with our tests, this is caused by the gradual change in diameter. As we saw, diameter is related to amplitude, and so when we see the bell attached here, these are pictures of a ripple generator. This is a ripple generator. It is basically a little foot right here that vibrates on a little water table, and there's a light up here in this general area that shines down, reflects on this mirror, and casts an image onto that screen there. And so what we have here is just a basic air cylinder. This is all of our didgeridoos except the one that we tested. for the bell effect. And this is an air cylinder with a bell on it. So as you can see here, they're nice linear waves. And then once they hit the bell, they start reflecting in a sort of a circular manner. And the reason why it increases impedance, increases in amplitude and pressure is because it's sort of acclimating the energy to the pressure outside the air cylinder. So when we have a bell end on here, these sort of come out like this. And how it acclimates it is since the impedance is decreasing, the impedance being the resistance to air, since it's decreasing as we go out, the amplitude is able to be much higher, and more waves are reflected, and more waves are, less waves are reflected and more are transmitted. So this is just a little thing that we did earlier, just kind of extra. I think this is called a horn, and so it's how the ends of trumpets and tubas are shaped. It's the more optimal version. So as you can see, there's an exponential curve on here, and that's so that the waves can get acclimated at a more effective pace that is increasing. And so a perfect horn would be the size of the room, so that it could acclimate it all the way before it changed pressure. So our conclusion, our hypothesis was correct. The length does have direct effect onto the frequency, and I don't think we explained this earlier, but so that is the reason behind that is because the wavelength of one wave of energy is 4 times the length of the air cylinder. And so if one wavelength is 1 hertz, and that's the frequency. So if you have longer waves, less frequency, and the diameter is linked to amplitude, because if you have a larger pipe, then that means that there are more particles to excite. And then for the bell effect, we just explained that. If we, as a part of our conclusion, if we had more time, we would have also tested the thickness of the pipe and to see what effect that had on the energy that it produced. And then also, if we had more time, so actually, let me explain this first. So the inside of the didgeridoo obviously isn't perfectly circular all the way through. It has imperfections because of the termites, because of its origins and the termites eating out the inside. So if we had more time, we would have filled the inside of the PVC pipe with a sort of expanding rough foam to sort of mimic that, that inside of the cylinder. So here are our sources, and here are acknowledgments. We'd like to first off thank Chris, our mentor, in the back there. He's really the one who let us know and taught us through all of this and got us access to labs and the ripple generator and everything.
And Chris also helped us play the didgeridoo and share our experiments.
And then also we'd like to thank Rebecca Kipp, our advisor. She helped us edit our papers and edit our poster and helped us get that all nice and proper. And then we'd also like to thank Dr. Seamak and Dr. Galovich in the physics department. They are the ones who gave us permission to get into those labs in the ripple generator, and they really also helped us to understand the concepts behind our project. And then obviously Christopher and Sophia, our RAs, we'd like to thank them as well for kind of managing the residential aspect of this, and then Noble Energy, and it was my sponsor for both the subjects that were being sponsored.
I'd like to thank my research sponsor, the Edward Mannequin Foundation. and also my sponsor for being here at FSI, the Rolly R. Kelly Family Fund at the Denver Foundation. And we'd also like to thank FSI, Lori Ball, head of FSI, and also head of Mass, Steve Anderson. And also, we'd like to thank the University of Northern Colorado for allowing us to have access to their facilities like maybe 3D printer and also rooms for us to put our box and do our experiments.
And any questions? Yes. Well, our mentor is back there, so if you want to, do you want to give a demonstration? Yeah.
So this like play it from here? Sure, that's fine. Oh, you guys come in? This is go for it. Did you